Hi everyone, welcome to this M2 Digital Talk. Today's speaker is Jonathan Hirst, and the talk is about predicting chemical reaction yield. Professor Jonathan is a full-time professor in the computational chemistry department at University of Nottingham. In 2020, he was awarded a chair in emerging technology by the Royal Academy of Engineering. His research focused on empowering the development of the next generation of molecules that chemical engineers and chemists make by using machine learning to augment human decision making. His tenure as head of school saw some significant transformation under his leadership, including the building of the GSK Carbon Neutral Laboratory and the successful bid for an Athena Swan Silver Award. Thank you so much, Jonathan, for accepting our invite to present here today, and looking forward to the talk.
Okay, well, thank you first, Prudencio, for the opportunity to share some of our work with everyone. So the main motivation for the research I'm going to tell you about and the research more broadly in our group is to make drug discovery a more sustainable process. The headline at the top there, waste disposal in the pharma sector for R&D is estimated to be around $20 billion per annum. And this is, of course, because going from known molecules to new desired target molecules is a challenging problem. And often the considerations on the bottom right here are secondary to actually being successful in the synthesis in the first place. So we are hoping to generate and make new machine learning and AI tools that will help chemists identify greener target molecules and greener, more sustainable routes to them. The University of Nottingham has a particular interest in sustainability and sustainable chemistry. And in the introduction, Prudencio mentioned the GlaxoSmithKline Carbon Neutral Laboratory, which was opened in 2016 on our Jubilee campus. It's the only building of its type in the world, carbon neutral over a 25-year lifetime with actual synthetic chemistry happening within it. It meets all kinds of sustainability credentials that normally only office type buildings can achieve. And this was funded in part by a generous gift from GSK alongside UK and government and charity monies. Just as important as the building itself, iconic though it is the researchers within it. And we have a number of constituencies who are very receptive to sustainable chemistry, including a centre in doctoral training. So it's a graduate programme funded by the UK funding body EPSRC on sustainable chemistry. We're involved in a prosperity partnership in collaboration with GlaxoSmithKline and colleagues at Nottingham and the University of Strathclyde and other drug discovery activities. So we want to persuade these various cohorts of chemists, synthetic chemists, that some of these computational tools will be useful in their day-to-day life, make life easier for them, and also encourage them to move to more green and sustainable practices. So the field of machine learning and its application in chemistry, enabled by, I think, several interesting developments over the last decade or so. There have been a lot of significant advances on the algorithmic side, maybe most prominently in a general sense, deep learning, and in a more specific sense, AlphaFold in in making more accurate predictions of protein structures. I've listed some other areas of algorithmic development that we're interested in. Data is another big enabler, and I think we're on the cusp of moving to a much more open data, open innovation paradigm, and this really will be then an area that machine learning can exploit. There's been very significant developments in hardware and in GPU technology and everything that goes around that in terms of software and libraries. Equally, technology and miniaturization is having a very significant impact in high throughput experimentation and the coupling directly of algorithms to experimental setups. Finally, collaboration is ever more easy, and I think different constituencies are talking to each other much more frequently as we see a convergence on some of these big challenges. So going to tell you about some of our ongoing work. In the area of machine learning, there's a variety of things we've been looking at. Not going to go through the whole list here right now. And for today, I'm just going to talk about a couple of projects within the prediction of chemical reaction yield. So the main story will be work that Alex, a student in the group, did on predicting the yield of amination reactions, focused largely on support vector machines. This is work funded by GSK and EPSRC. Alex is just coming to the end of her PhD and will be looking for a job soon. But before I tell you about that in detail, I wanted to spend a little bit of time on some other work. Joe, a newest student in the group, has been collaborating with an SME, Deep Matter. And this is also focused on reaction yield prediction, but based on time series data generated by sensors that one inserts into the reaction. So Deep Matter manufacture this sensor equipment and shared with us some data from that. And the idea in a nutshell is fail fast, fail cheap. Yeah, so if something's not working out and you can spot that early, that's a time saving. Research is all about failing and learning, and if you can accelerate that process, there are big wins to be had there. So let me tell you a little bit then about that first, before turning to Alex's work. So the sensor setup involves a head that gives a measurement of ambient pressure, some sensors that are exposed, giving measurements on UV light and temperature, and then some immersed sensors. And what one gets out then is a sort of time series set of data corresponding to each of these sensors. And the website there links to Deep Matter and their products called digital glassware, and is integrated into the data management system hosted on the cloud. So the data that Deep Matter shared with us were 15 repeats of the same Buchwald reaction. That's the chemistry shown here, and it's similar chemistry that will feature in the work with Alex that I'll tell you about as well. So the reactions are monitored with the sensors. Chromatography data recorded at 30-minute intervals, and that's taken as the sort of ground truth of the measurement of yield. And the idea then is to predict yield or product formation from the sensor data. So real world data is always challenging, and when we came to look at it in more detail, there was some missing data. So we were in fact looking at 10 repeats rather than 15 repeats. There was some variation in the solvent, which again, which became moot once this missing data were revealed. So that's the data set. You can see the range in yield from, I guess, around 10% up to around 90, but that dynamic range was reduced somewhat once we spotted the missing data, but there's still a decent range of yield for us to work with. So the raw data looked like the panel on the right, the individual runs shown in black and the average in thick red line. And we have then two approaches I'm going to tell you about. One is very sort of off-the-shelf regression, decision tree type approaches based on features from the sensor data themselves. And then the other approach recognizes that we're dealing with time series data rather than fully independent measurements at different times. And so we've looked at a recurrent neural network approach in this case. So the feature data are recorded at pretty short time intervals, whereas the chromatography data only every 30 minutes. So we needed to make that more uniform and downsample the sensor data and perform some linear interpolation on the HPLC data to upsample there. So we're looking at about 2,000 or 3,000 instances per run and 10 runs. So if we look, for example, at the RGB data as a function of time, we've got the three different components. And what happens is the reaction proceeds from a sort of creamy color where I guess you've got a little bit of RG and B present. Oh, hand up. I'm happy to take a question.
Yes, so I'm not sure I fully understand the data part, the previous slide. So you have only one reaction type and one reaction type, but then multiple reaction, meaning the reactant and the product are different, like from run to run.
Yeah, so there's one piece of chemistry that's being performed, and the idea is that even the same chemistry in different people's hands doesn't always happen the same way. So a better chemist might be more careful or remember everything or whatever, and the reaction proceeds more robustly. Another case, chemist might be, or some external factor might intervene, and the chemistry might not go as originally anticipated. So even that we've basically got 10 repeats of the same chemistry, but done by 10 different chemists.
Okay, and in the data set, do you have many different chemistry or just one chemistry?
Just one chemical reaction. All the conditions were supposed to be the same.
Okay, cool. Perfect. Thank you.
Yeah. Okay, so we can see that if you look at the reaction, it goes basically from a cream color to a black color, and these RGB components attenuate over time. And this possibly corresponds to the palladium, the activated palladium-2 catalyst coming palladium-0, which is black. So we can look at correlation between the different features and the features with product formation. So we've got product shown here in this row and at the top here. And clearly from those curves we just looked at, we know over time there's a sort of cumulative change. So we looked at these cumulative features, and some of them are clearly highly correlated with product formation. So this sort of guided us in the next steps. So treating this as a regression problem, we looked at then using this green cumulative feature in a univariate analysis, a transformed version of it, which I'll talk a little bit about, and then a fully multivariate problem with and without the color features. And we're going to use mean absolute error to assess the models, with obviously a lower error being better. And because the value itself is a percentage, these errors are going to be reported as percentages, but they are mean absolute errors, not relative errors. Okay, so linear regression has a number of assumptions, and some of these are shown here. And an interesting mitigation is that one can perform a power transformation, a so-called Johnson transformation, that can help correct some of the or move your data closer to the assumptions underlying that you'd want to hold for a linear regression to work. So this power transformation shown up here will make your input data look a little more normal. So then there are challenges on the nature of the noise and collinearity between the features. So the other set of models we looked at then were based on decision trees, so random forest and gradient boosted regression. And we can see some of the key results here then on the right. So a lower number is better. The baseline is, well, if we just predict everything to be the mean observation of product yield, that would give us a mean absolute error of 7%. So we want to be smaller than 7% to be achieving anything significant. And we see polynomial regression using the green cumulative descriptor achieves a mean absolute error of about half, so 3.6. And this is relatively similar to what linear regression achieves on the Johnson transformed feature there. Okay, so let me turn to the time series treatment of the data, which is going to be based on recurrent neural networks. We're probably all relatively familiar with the inspiration for artificial neural networks taken from biological neural networks or brains, with the idea that the inputs are the neurons, and then the synaptic connections correspond to a weighting function, and as the neuron fires and goes through the synapse, an activation function is applied, which determines whether the connected neuron receives a signal or not. Then these weights are the free parameters in the algorithm that are optimized during training. So that sort of process would correspond to this well-known architecture, this sort of feed-forward neural network, where you have an input layer, a set of hidden layers going on to an output layer. And in recurrent neural networks, there's a sort of feedback loop, that the output from the hidden layer is taken as an input again. And without going into any of the detail, it turns out these LSTM architectures have been very useful in modeling time series and natural language processing types of problems. So, I mean, what I talked about previously was taking a snapshot out of those sensor data measurements and saying, can we estimate yield at that point in time from the data that the sensors have just reported then? What we're trying to do now with the LSTM is say, well, I've seen this sensor data up so far. How's it going to go? Can I predict the future, you know, in the next 20 minutes or next hour or the next 2 hours? So we have first an LSTM that predicts the current product data from the previous 20 minutes of sensor data, and then a second LSTM that uses the previous 2 hours of predictions from the first LSTM to predict ahead by one of these amounts of time, 30 minutes, 60 minutes, 2 hours. So, well, and we see the error there, remembering that baseline of 7% as a mean absolute error would be what you'd get from a very simplistic model. And we can see, obviously, as one might anticipate, the further into the future you go, the harder it is to predict things, but we're still substantially below that 7% threshold. So that looks quite encouraging. So just to summarize this work, we demonstrated the effectiveness of LSTM in time series analysis. And obviously, there are opportunities to extend this to different reaction data sets. I guess that might have been behind the question earlier, and different sensor types. So the manuscript should be accepted shortly by Journal of Molecular Graphics and Modeling. We're just making some requested revisions, but it's out on the preprint server if you want to see some of the detail. Okay, let me switch then to the sort of advertised abstract. Using kernel methods to predict reaction yield, as I said, work led by Alex in the group in collaboration with GSK. So performing reactions is expensive, time-consuming, resource-consuming, and clearly an impact in terms of the sustainability of your chemistry. Finding the ideal reaction conditions is a challenging multidimensional problem. There can be some hypersensitivities, and often you don't have a systematic set of data, which makes the application of machine learning methods difficult. High throughput experimentation offers some hope here, where one performs a matrix of parallel reactions under varying conditions or varying reaction components. So I shall excuse me. I possibly have a slight cold coming on, but it's not too bad at the moment. Yeah, so I'll walk you through this, tell you a little bit about the data set, the molecular descriptors, the support vector regression approach we've adopted, what the key findings were, and some further prospective experiments that we suggested. So data set and molecular descriptors. First, the data are publicly available, but published by Abigail Doyle's group in Science in 2018. And it's again the Buchwald-Hartwig amination. So there are about 4,000 different reactions done in a high throughput experimentation setup where one has a combinatorial data set constructed as follows by varying 4 of the different reaction components. So there are 15 different aryl halides here, where the R group varies, and the halide might vary. So this R group was things like trifluoromethyl ethyl, methoxy substituents, and there are also some 2 and 3 substituted halopyridines. Perhaps somewhat unusually, the reaction also features additives that might be inhibitory. So one of the key questions for this chemistry was, we want to use it in a drug discovery process. Many candidate molecules have this type of isoxazole moiety in them, which is interesting from a potency point of view, but might negatively impact this cross-coupling reaction. So there's a motivation to understand if one could predict the impact of this fragment, the presence of this fragment on the chemistry. So it's a little bit of an unusual setup in terms of you're not just making a variation hoping it will make the chemistry better. This is trying to understand when we've got some important molecules, what chemistry is going to perform best. Then there were several palladium catalysts where the ligands of the phosphorus vary, and 3 different bases. Okay, so we're looking at several sets of descriptors. I'll walk you through these. 1, hot encodings, which are an important baseline. Some quantum chemical descriptors, which were described in the Doyle paper, and might intuitively feel like they're the most information rich and the sort of descriptor set of choice to reach for. And then I will tell you about the descriptors we looked at in some detail, fingerprints and kernel descriptors. So a key question usually in many machine learning applications, have I learned anything of actual physical significance? Often machine algorithms are sort of agnostic to the types of information that are present in the data, and there might just be some underlying structure in the data which has nothing to do with the underlying science, which nevertheless the algorithm captures. So one can test for this by using this simple binary flag for presence or absence of a moiety in the reaction. So there's no encoding of any chemical information or any relationship between one entry in the vector and a different entry in the vector. So it's a simple on-off, one-hot so-called encoding, and its major limitation would be if you've got a molecule with a combination that's not in the training set, you won't be able to make a prediction on it. The quantum chemical descriptors were 120 different descriptors based on a set of different sorts of properties. So sort of whole molecule descriptors like the HOMO and LUMO energy, some atom specific properties like partial atomic charges, and then also some calculated vibrations of subgroups present in the molecules. So that descriptor set looks something like this, with a total of 120 elements in the descriptor vector. So I think These are obviously well founded, potentially informative and robust and information rich, but they're probably the most computationally demanding to calculate, which might not be an issue for relatively small molecules or relatively small data set, but might be an issue if you want to do much larger scale screening. And maybe more serious than that, for example, some of these shared molecular vibrations, if you move too far away from the training data, then you're in danger of not having the common substructure present, and then your descriptor vector can't be completed, and you've got a problem in generalization. So graph-based descriptors are also probably familiar to you. One thinks of the atoms as nodes in a mathematical graph and bonds as edges, and one can compute various kernels or similarity matrices from these graphs. So each component, the aryl halide, the additive, the base, the catalyst, are represented by a graph. One computes a kernel for each of those reaction components, and then takes the element-wise product, or the Hadamard product, as it's known, of the kernels to get an overall representation. So it's very quick to compute and applicable to any molecule. The downside is it only contains topological information about the connectivity. And finally, fingerprints. These should also, I think, be relatively familiar. The vectors of binary bits corresponding to presence or absence of substructures, and very well known variants, Max, RD kit, and Morgan fingerprints. And we looked at a variety of bit lengths and didn't see any improvement over 512. So looking at 512 bit length fingerprints. Again, each component represented by a fingerprint, and we can then either concatenate these into a reaction level representation, or we can calculate a Tanimoto similarity or kernel for each component and then combine those together, much like the Weisfeiler-Lehmann kernel in the preceding slide. So again, quick and widely applicable, and again, only containing topological information. Okay, let's turn to the support vector regression. I won't really say too much about the detail of support vector machines. They're pretty well established in the literature over the last 2 or 3 decades. One has a choice of a variety of hyperparameters, including the choice of the kernel, which one is using to transform the data into a high dimensional feature space, where you can then make a separation with a linear hyperplane effectively. So in this plot, we've got in this table, the different representations or descriptor sets, the one-hot encoding, quantum chemical properties, and the fingerprints and kernels, and then kernel descriptors, and then across the top we've got the different kernels. And the Tanimoto kernel is effectively then a pre-computed kernel, and similarly the Weisfeiler-Lehmann approach, but one can look at putting a nonlinear transformation on top of that, which we did and didn't find any particular benefit. Okay, so cutting to the chase. Well, just before we show the results, one important consideration is how one does the assessment of predictive accuracy. And if one simply takes those 4,000 examples and sort of randomizes them and tries to do some predictions there, the results are generally not so good. One has to think, and the most important component is the aryl halide with the greatest amount of variation. Think about doing a sort of stratified sampling. So going to calculate the mean yield of the reactions for each aryl halide, and then use that mean yield to rank the aryl halides from best to worst. We're going to take the two endpoints out and include them in the training data, and then construct 3 test sets where we leave out every reaction involving some number of the aryl halides. So the first test set takes out aryl halide 7, 5, 3, 8, and 9. And then the next one is a slightly different stratified sample and a third test set there. So this, the original science paper excited quite a lot of discussion in the literature about how much information was simply encoded in the location on the plate, or the plate in which the high throughput experimentation was done. So this issue of constructing a careful test set for a robust estimate of predictive accuracy is quite an involved but important issue. Okay, so this is the summary slide of the performances. One has got on the different rows the descriptor set, so TAN short for Tanimoto, FPS short for fingerprints. Then we've got the variety of kernels. So the pre-computed kernel corresponds to Tanimoto, and the vice versa Lehman, where which is equivalent then to the linear approach. So there's no data in that in those first few rows of the first column, and conversely, no data in these last few for the fingerprint and the quantum and one hot. So sort of pink to blue or small to large gives you a sense of the predictive accuracy based on the coefficient determination. We can see that one hot and quantum don't do so well, and in fact the R squared was effectively random here for quantum on the linear and the polynomial kernel, and we can see that the fingerprints and the Tanimoto and the vice versa Lyman representations do pretty well. So we can see what that looks like in terms of a plot of all the predictions following that careful test set construction, and we can see that the errors, the mean error in the predicted yield is lower in these cases on the right-hand side, and the correlations are higher. One interesting general feature is that it's difficult to predict the higher yielding reactions, which are obviously the ones of most interest. And this arises because, well, we can see it again here as we go from the low yielding reactions to the higher yielding reactions, the root mean squared error, the predictions increases. And this is basically because the low yielding reactions are the majority of the training data. So in future work, one might want to think about upsampling the higher yielding reactions. It's maybe not quite trivial to do. So we can see a sort of inverse correlation between accuracy of prediction and amount of lack of data in the training set. Okay, then we wanted to do some prospective predictions, and the idea was ultimately that measurements were going to be made at GSK on their mosquito robot. That proved to have a few technical challenges which weren't resolved before COVID struck, and then we were impacted by that. So these prospective predictions remain to be tested. So what we've done is taken the best predictive models and looked again at the aryl halide ranking. So with these different combinations of descriptors and support vector regression approaches, and we wanted to look at a couple of aspects here. So with the greatest variation in the aryl or heteroaryl halides, we're not so interested in the inhibitory effect of the additive. So we basically just took the most active additive. We looked at a couple of catalysts. Okay, so sorry, just going back. The aryl halides, 5 were in the initial data set and 54 were new. The most high yielding additive from the original data set, 2 of the original palladium catalysts and 1 new one, and 2 of the original bases and 1 new one. So primarily looking at some hypotheses around which aryl halides might be most high yielding. So this combination led to about 1,400 proposed reactions, and we trained on relevant data from the original data set, including the additive control reactions. And then there was a second set which was smaller, because we wanted to do the explicit calculation with the quantum chemical descriptors, but our variation in aryl halide was went beyond the structural features that the quantum chemical descriptors could cover. So you're looking at a specific vibration, and that's a descriptor, but you haven't got that functional group in. Those they would largely defined on 4 contiguous atoms. If they aren't present in your new molecule, then obviously you can't compute the descriptor. So this second set was smaller, but allowed comparison with the quantum chemical descriptors. And here we see the range of predictions, and we'll maybe just pick out a couple of features briefly. The first is that the one-hot encoding predicts a lot of catalysts with no activity, which is, sorry, a lot of combinations, a lot of reactions with no activity, which is just a limitation of the one-hot encoding. The quantum chemical descriptors have a relatively narrow range of predicted yield, whereas the more accurate approaches actually give a wider range of predicted yield, which was quite interesting. And some of those 54 new aryl halides were chosen to as ones that might improve the yield. Okay, so I see time is pressing on. Maybe I'll skip this last slide and just move to a summary. So we've got our different sets of descriptors, and we can See, the quantum chemical ones are based on calculated properties. Fingerprints and the Tanimoto kernel descriptors are based on a local topology. The Weisfeld alignment kernel descriptors based on a global topology, and then the baseline is a simple flag present or absent of the chemical moiety. Obviously, that's quickest to compute, and the quantum chemical descriptors are slowest to compute, but I think more challenging than the speed of calculation is the applicability, unless one chose a more selective set of quantum chemical properties. They aren't so generically applicable, and we found in the conjunction with the support vector regression that the quantum chemical representation was not as generalizable as the fingerprint and Tanimoto descriptors. So just to finish, I have a couple of adverts. So one is a book in a Royal Society of Chemistry series that I edit. So a lot of nice sort of pedagogical overviews in the chapters in this book, including one that Alex wrote. So that's one advert. And the second is we've been recently funded by Innovate UK to help an SME colorifics on a machine learning challenge to really develop some machine learning infrastructure to design new natural product dyes. So if that is of interest, you should be able to find it advertised on the Nottingham website. So with that, let me just acknowledge the people. There's a lot going on in the group, and I've just talked about a particular focus. So the work with the sensor data done by Joe here on the right, and the work on the support vector regression done by Alex. Joe's been collaborating with David at Deep Matter, and Alex has been collaborating with colleagues at GSK and in data science at the University of Vienna. And with that, I shall stop. Thank you for your attention, and I'm happy to take any questions.
Perfect. Thank you so much, Jonathan, for the talk. If you have any question, please raise your hand and open your mic to ask a question. But there was a question in the chat just seen by Jay Lee, asking if the analysis performed in this study, I think it was during the first part of the talk, if the analysis was designed for one specific chemical reaction.
And the answer to that is, I mean, it wasn't bespoke designed to be only applicable to one reaction, but the data set we had was only for one reaction, and obviously one would want to test the generality of the approach on different reaction data, and we're talking with Deep Matter about that.
Okay, thank you. On the conclusion on the second part of the talk on how quantum properties don't generalize quite well compared to more structural properties. Do you think is a matter of the type of property that you have included in the study, or you have also tried different type of library to get different type of quantum properties, and anyhow they don't just generalize?
I think the main issue is around specific vibrations. So from a sort of chemical intuition point of view, one knows that certain bonds are breaking, for example, in the reaction, and it therefore might be interesting to look at the vibrational properties of those specific bonds. But as you try and incorporate more specific knowledge about the reaction, then one is losing a certain amount of generality. So that's the challenge. So as you decorate the aryl ring and the aryl halide differently, you might suddenly move beyond the initial scope that may have been chemically well motivated, but kind of sets a horizon in terms of how much data can be explored in that approach.